Welcome to lecture series on the course Foundation of Mathematics. In this session, we will discuss the two kinds of functions, injective and surjective functions. So, let us begin this session by starting with the injective functions. Now, injective function is also called as a 1-1 function. So, we say a function f from x to y injective if for each pair of points x1 and x2 in x with the property x1 not equal to x2, their images are different. F of x1 is not equal to f of x2. In general, the two distinct pair in x will map to will have a different image. So, they will map to a distinct point in y. So, if such a function, if such things happen, then we say that the given function is 1-1, or it is also termed as 1-to-1, or it is also termed as injective function. So, we write this using quantifiers. F from x to y is 1-1 if and only if for any 2 points x1 and x2 in x with the property that x1 not equal to x2, because if x1 is equal to x2, they are going to have a same image intuitively. So, f of x1 is not equal to f of x2. So, that is okay. Now, here we want to write this exactly in terms of set of context. So, what should be the set of context? We are taking a pair. So, we can think of ordered pair from the set x cross x with the condition that the first coordinate is not same as the second coordinate. So, we take that kind of ordered subset of x cross x. So, let x be the set of all the element of the form x comma y which belongs to x cross x. So, that means x comes from capital X and y comes from capital X again with the property that x is not equal to y. So, using this S, I can say that now function f from x to y is 1-1 if and only if for all x comma y in this S. So, when I say that x comma y is in the set S, definitely x is not equal to y, and x and y are coming from the set X. We have the property f of x is not equal to f of y. So, if this satisfies for every element in S, we say that the function is 1-1. One immediate example of 1-1 function is a function from x to x defined as f of x is equal to x identity function. This is a very trivial example because if I take any 2 points x1 and x2 in the set of x with the property that x1 not equal to x2, this would imply that f of x1 is not equal to f of x2 because f of x1 itself is x1 and f of x2 is itself is equal to x2. So, if the 2 points are distinct, their images which are same respectively are also distinct. So, this is one immediate example. Some more examples of 1-1 function is this: f going from 0 comma 1 open interval 0 comma 1 to r defined by f of x is equal to 1 by x. So, we prove this 1-1 function. So, let x1 and x2 be in the domain with the property that x1 not equal to x2. We need to show that f of x1 is not equal to f of x2. So, if x1 and x2 belongs to 0 comma 1, definitely x1 and x2 cannot be equal to 0. So, since x1 and x2 belongs to 0 comma 1, this implies that x1 and x2 not equal to 0. I mean, I want this because I want to define 1 by x1 and 1 by x2, and therefore 1 by x1 and 1 by x2 are very well defined real number. Now, if x1 is not equal to x2, then this directly implies that 1 by x1 the fraction is also not same as not equal, and therefore, this says that f of x1 is not equal to f of x2, proving that f is 1-1 or injective. Next example, f of x is equal to x cube, where the function f is defined on R to R. The domain is a set of real numbers and the codomain is set of real numbers again. So here to observe the domain and codomain is also important, because changing in any of this may convert the given function 1 or may convert the function. If the function is 1 it affects the 1-1ness of the function. So this function, as you all know, it's an odd function. Okay, so how do I show that? If I take any two pair in R, distinct pair in R, their f of x is also, their images are also distinct. Okay, so we observe this first thing. Let x comma y be 2 points in R such that x is not equal to y. So first thing, we observe that x cube minus y cube, this expression can be written in terms of x and y. So x minus y into x square plus xy plus y square. Now we know that this x minus y will never be equal to 0, since x is not equal to y. So this will be equal to 0 provided this x square plus xy plus y square is equal to 0, and this is not equal to 0 if this is not equal to 0. So that's how we would prove. So how would I show that this x cube, okay, for this x not equal to y, I need to show that this x cube minus y cube is x cube minus y cube is not equal to 0, that which would say that x cube is not equal to y cube, which in turn implies that f of x cube is not, f of x is not same as f of y. So I discuss this into the cases. The first case is when x and y are of same sign. So that is either they are positive or x and y are negative. When this thing happen, x square and y square are strictly greater than 0 and xy also strictly greater than 0, and therefore x square plus xy plus y square is strictly greater than 0. If I call this as star, so from star, therefore x cube minus y cube will never be equal to 0. So that is going to be either strictly greater than 0 if x minus y is strictly greater than 0, and if x minus y is strictly less than 0, then it's going to be strictly less than 0, as we know that x minus y is non-zero because x is not equal to y. The rest two cases, that is when one of them is one of x and y is 0. So if I say, if without loss of generality, if I say, because same argument can be done for the other, because this is divided into two sub cases, that is when x is equal to 0 and y is non-zero. See, if one of them is 0, the other one have to be non-zero. So without loss of generality, if I assume x to be equal to 0, then y is non-zero. So therefore x cube is equal to 0 and y cube will be non-zero as y is non-zero. This says that x cube is not same as y cube, and therefore f of x is not same as f of y. And the last case is when both of them are of opposite sign, x and y are of opposite sign. So that is when x is positive and y is negative, or x is negative, y is positive. So no matter in which category it falls, we know that x square is always be positive, y square will always be positive, as well as xy. So if they are, we don't use this at all here in this case. If x and y are of opposite sign, directly we can say that x cube and y cube are also of opposite sign. So this implies that x cube and y cube are of opposite sign, because we know that x cube and y cube are odd function. F of x equal to x cube is an odd function. So if x and y are of opposite sign, then x cube and y cube will also be of opposite sign. In fact, x cube will have the same sign as x and y cube will have the same sign as y, and therefore they are going to be opposite sign, and therefore we say that f of x is not equal to f of y. So in all three cases we have shown that no matter what x and y you take, because this three case exhaust all the possible x y's from the set of real numbers. So no matter what x and y you takes which are distinct, then f of x will not be same as f of y, and therefore the function f is 1, 1. So a very important proposition, in fact it's as same as the definition, it says that the function f from x to y is 1 1 if and only if for any x1 comma x2 in x, f of x1 is equal to f of x2. That is, whenever the image of any 2 points are same, this should imply that x1 is equal to x2 if the function f is 1 1. So that is straightforward to the definition of the function being 1 1. So let me take any 2 point x1 comma x2 in x. So I want to show that f is 1 1 if and only if this condition is true. So when this condition is true, f of x1 is equal to f of x2 implies x1 is equal to x2. We know that this is equivalent to saying it's contrapositive. So that is, x1 is not equal to x2 implies that f of x1 is not equal to f of x2, and this is exactly the definition of 1 1ness. You have any 2 points x1 and x2 in x. So whenever x1 is not equal to x2, that implies f of x1 is not equal to f of x2. This is same as saying the function f is 1 1. And this is an important result. We can most of the time we can go from here to here directly. So we have one example, f of x is equal to 3x plus 2, and this is a 1 1 function. We claim that f is 1 1. Using propositions, it's very easy to see. Let x1 and x2 be 2 points in the domain such that f of x1 is equal to f of x2. So we want to show that x1 is equal to x2, then we are done. Then we in fact show that the function is 1 1. So this implies 3x1 plus 2 is same as 3x2 plus t, and by simple algebra of real numbers, you can show that x1 is equal to x2. Plus 2 gets cancelled, and same 3 is non-zero, 3 and 3 gets cancelled. So this says that the function f is 1 1. Now the question is, when do we say that the given function is not onto? So it's by the definition, it's trivially true that if I can find 2 points in the domain x1 and x2 which are distinct but they have the same image, then in that case the function is not on 1 1. Okay. Now we have seen the compact definition of the function 1 1 with the help of quantifier. So using that, in fact, we can have this argument. So we know that f from x to y is 1 1 if and only if for every point in the set of context L, right, for every point x comma y in the set of context S, where S is set of all the point x comma y in x cross x, such that x is not equal to y, we have f of x is not equal to f of y. I can change the notation, instead of x and y I can take x1 and x2 as I have taken here. So if I can find at least one point in this at least one pair in this S having this condition, that is x is not equal to y, but f of x their images are same, then the function is not 1 1. So how do we write down this? F from x to y, so it's exactly the negation of this statement, is not 1 1 if I can find a point x comma y in S such that f of x is equal to f of y, as simple as that. So these are those 2 points. So whenever we have such things, and the function is not 1 1. So whenever we say that there exists, you should be able to produce 2 points in x which are distinct but have a same image. So to show that the function is not 1 1. So one example here, f from R to R. This is a very interesting example because here in this case the domain is also plays a crucial role, and I am going to show you how the change of domain would affect the injectivity of the given function. So if I take this as the domain f from R to R defined by f of x is equal to x square, then the given function is not 1 1, because you can see, because the domain is varying over the whole real number. So you can take the negative as well as the positive real number, and in fact if you take x to be equal to -2 and y to be equal to 2, x is not same as y, but you can see that f of x which is equal to -2 the whole square, which is same as 2 square, that same as f of y, and they are same. So this says that f is not 1 1, right. So if you succeed in producing at least two distinct pair, in the domain such that their image is same, then you say that the function is not 1 1. So that comes to the observation, the geometrical observation of the graph. Now if I change the domain of this function from R to 0, close interval 0 comma infinity, then this function, what can you say about this function? The same function f of x is equal to x square. Is it 1 1? Definitely it is 1 1, because you are not consider the negative part of the real number. So for that matter, you can also consider minus infinity comma 0, either the negative positive, because that is creating a problem. You can see that just like here, the graph of this function is something like this. So symmetric point maps to the same point on the positive x-axis, from the positive x-axis, from the negative x-axis. When I consider the domain as only 0 comma infinity, then I am considering only this part of the graph, not this, and therefore this is always positive. Okay, so therefore this is always 1 1. That you can very easily show using the proposition. So suppose I have f of x1 is equal to f of x2, that is same as x1 square is equal to x2 square. Being x1 and x2 are positive, I can directly say that x1 is equal to x2 as x1 and x2 greater than or equal to 0. Okay, so this shows that the function is 1 1. This function is 1 1. So this is how the domain or the codomain, in fact the domain plays a crucial role while discussing the 1 1ness of the function. Now how we let's understand the 1 1 function graphically. So given a graph, when can we say, given a graph of function, when can we say that it's a graph of a 1 1 function? So that's determined by every horizontal line. Okay, like in f of x, okay, we just take an example of a function which is not 1 1. So that is f of x is equal to x square. Now you can see that if I draw a line parallel to x-axis, say from this y value, then this x1 and x2 are distinct, but they have the same image, that is y, right? So f of x2 is equal to y and f of x1 is equal to y. So this makes a graph not 1 1. Okay, so how do we see that, okay, what should be the negation of this? So if I can find, so that means over here I see that there is this vertical, this horizontal line which is passing to the point x equal to which is passing to this point y, okay, that is 0 comma y, parallel to x axis. This line is actually same as saying x equal to 0, right? So that passing to the line, a parallel line to x axis which is passing to the point 0 comma y, intersects the graph at least twice. So in fact if it intersects more than that, again we would have some more points having the same image. So that violates the injectivity of the function. So therefore a function f from R to R is 1 1 if and only if every horizontal line intersects the graph of f at most 1. So it should not intersect the graph more than 1. It may not never intersects the graph. It may never intersects the graph. In that case, that is not a part of the y axis, that y values is never a part of the range of the given function. That is possible. Okay, so this is how we understand the 1 1 function graphically. So if every horizontal line intersects the graph of the function at most once, then we say that the given function is 1 1. So now let's talk about the surjective or onto function. A function f from x to y is said to be onto or surjective if for each y in y. So we have a function like this. This is my x and this is my y. So if for each y in y there exists x in x such that y is equal to f of x. In other words, every point in y has a pre-image. Every point in this codomain has a pre-image in x. Okay, so that kind of function is called as an onto function, And one trivial observation one can do over here is that the range of this kind of function is the whole codomain. So, how do we write down? So, we will prove this shortly. So, how do we first write down this in terms of quantifiers? So, f from x to y is onto, just try to understand, just split this in terms of quantifiers. So, try to understand the quantifiers involved over here. If for every y in y there exists x in x such that x forms a pre-image of y. So, such that y is equal to f of x. So, there are two quantifiers involved and the property is y is equal to f of x. So, one observation that we make over here, that if f from x to y is onto, then range of f is the whole codomain. In fact, we already know that the range of f is a subset of y. We just need to show that y is a subset of range of f, and that is really true through the definition. We assume the fact that the function is onto. So, if I take y in y, being function is onto, that assures that there should be a point x in x as that f of x is equal to y. Okay. So, let y be in y. Since f is onto, and there exists a point x in x which acts as a pre-image of this y. So, such that f of x is equal to y. This is exactly the definition of a range of y being in the range of f, because range of f is a set of all point in codomain such that y is equal to f of x for some x in x. So, if you can find for a point y in y, if you can find a point x in x such that y is equal to f of x, then we say that y belongs to range of f. So, this says that y belongs to range of f, and therefore, we have shown that y is a subset of range of f. So, using this 1 and 2, you can say that range of f is equal to whole codomain. Let us look at the same example f from R to R given by f of x is equal to 3x plus 2. The question is this a onto function? Now, this would be onto function provided, see, I have a function from R to R. Provided I take any point y, I should be able to find x in this R such that 3x plus 2 is equal to y. So, that means for every point in this R, for every real number R, this equation should be solvable. That is very trivial because this is a linear equation and we can find the value of x for such y and explicitly. So, the claim here is that f is onto. So, how do we show that? Let y be a point in the codomain R. Now, this y I am taking from here, codomain. So, let y be a point in the codomain. I want to show that there exists x in x, x in R such that f of x is equal to y. So, we want to show there exists x in x such that f of x is equal to y. That is, we want to show we want to prove that says that 3x plus 2 is equal to y. Okay. So, now you just evaluate that x can be in terms of y also, it is dependent on y also because y is the first choice of real number. So, whenever 3x plus 2 is equal to y, this implies that x is equal to y minus 2 upon 3. So, we want x in such a way that it satisfies this equation. So, if I put x to be equal to y minus 2 by 3, definitely it is going to satisfy this equation because I have derived it from the same equation, and this is a real number. It is a very well defined real number. So, if y is equal to 1, x is equal to 1 minus 2 by 3. If y is equal to 2, then x is equal to 0, and this goes on. Okay. So, therefore, we succeeded in producing a real number x which is equal to y minus 2 for this y such that f of x is equal to y. So, therefore, there exists x. Okay, I will write down a complete statement. Therefore, given y in R, there exists x in which is equal to, in this case, y minus 2 by 3 in R, such that f of x, that is 3x plus 2, is equal to y. Okay, and therefore, we say that f is onto. So, that is enough to show that. Okay. Now, the question is, when the function f is not onto? Simply negate the definition, but if you have understood the geometrical view of onto function, then you can very easily look at this picture and frame the definition for the function which is not onto. We say that the function is onto if for every point in y there is a pre-image. So, if you can find at least one point in y which do not have a pre-image in x, we are done, then the function is not onto. So, first we would write down the definition of onto function and I will negate the definition of onto function to get the function which is not onto. So, f from x to y is onto if for every y in y there exists x in x such that f of x is equal to y. So, therefore, f from x to y is not onto if you can produce an element in y such that given any x in x, it will never be an image of any point in it will never be an image of that point. So, f of x will never be equal to y. Okay. So, given you are able to produce element in the codomain such that no element in x forms a pre-image of that particular point. Let us see some examples. F from 0 comma 1, the domain is 0 comma 1 to R, defined by open interval 0 comma 1, defined by f of x is equal to 1 by x. The question is this an onto function? See, you need to produce an element in R in the codomain which do not have, I mean, you need to observe whether there is an element in R which do not have a pre-image. Now, that is trivial in this case because we know that 0 cannot be expressed in this form 1 by x. So, you go ahead with 0, right. So, you go ahead with 0. So, let me take let 0 which is a point in y, consider y equal to 0. I want to show that no point in x, no point in the domain 0 comma 1 will form a pre-image for this 0. Okay. So, that is f of x is not equal to 0 for any x in 0 comma 1. So, we show this by contradiction. If there exists say x1 in 0 comma 1 such that f of x is equal to 0, then we are expecting to get a certain upset result. Okay. So, that is 1 by x1 is equal to 0. This is what we have. Now, I can multiply throughout by x1 provided x1 is non-zero, and since x1 belongs to 0 comma 1, this implies that x1 is non-zero. In fact, it is strictly greater than 0, and therefore, from star multiply x1 throughout, we have 1 is equal to 0, and that is a contradiction. So, this contradiction tells us there is no such x1 in the open interval 0 comma 1 says that f of x is equal to 0, and therefore, f of x is not equal to 0 for any point in the domain 0 comma 1. So, only that 0 I think is creating a problem here, right. Okay. So, I am sorry for this scratch work, and this says that f is not onto. Let me look at one more example. Yes, f of m is equal to m square, and f is different from the set of integers to set of natural number with 0 in it. So, we have something like this. This is a set of natural number, sorry, n with union. So, I would start with 0, 1, 2, 3, 4, 5, 6, 7, and this goes on, and this will have 0, minus 1, minus 2, minus 3, minus 4, 1, 2, 3, and this goes on. So if you see the mapping of each of this point, 0 will map to 0, minus 1 will map to 1, 1 will map to 1, minus 2 will map to 4, 2 will map to 4, minus 3 and 3 will map to 9 somewhere here, and this goes on. So you can see that there are gap in this. There are some numbers, there are some natural number in fact which do not have a pre-image, like 2 do not have a pre-image in this case, because square of any integer is never 2. You cannot find any integer whose square is equal to 2, okay, and therefore these 2 do not have a pre-image. So that's enough to say that the given function is not onto. Now you can also take 3, you can also take 5, because they do not have a pre-image, but proving that 2 do not have a pre-image is much a simpler task than proving that any other natural number do not have an integer. Okay, so what we do is that we consider a natural number 2. So we will show that 2 which belongs to n union in the codomain does not have any pre-image. So this 2 is our choice. Okay, now this I would, so that is I need to show that f of m, that is m square, will never be equal to 2 for any m in the domain set. This is what we want to show, that is to prove that this is to prove. Okay, so what we do is that this m is varying over the set of integers. So what I'll do is that I will consider every integers, and for this every integer I am going to show that f of m is not equal to 2. How do I do that? So I have a line, integer line, say 0, 1, 2, 3, 4, and this side minus 1, minus 2, minus 3, minus 4, and this goes on. So I will divide, I will split this set of integers or the integers into two parts. So I will do the partition. I will consider minus 1, 0, 1 in one part, and I know for this integer its image is either going to be 0 or 1, because minus 1 and 1 is mapped to 1 and 0 is mapped to 0. And the second case, I would consider all those integers which are greater than or equal to 2 and less than or equal to minus 2. That same as saying that its magnitude, its modulus is greater than or equal to 2. So I have two cases, and in that case also I am going to show that its image is not same as 2. So I divide this into two cases. Case 1, when m belongs to minus 1, 0, 1, this set. So in that case m square will either be equal to plus 1 or it will be equal to 0, 1. That is same as saying f of m will be 1, 0, and that same as saying f of m is not equal to 2 in this case. Now case 2 I will take when m belongs to z such that mod of m is greater than or equal to 2. So in this case I am taking all the remaining integers. So if mod of m is greater than or equal to 2, f of m, that same as m square. So m square, as we know, is same as mod of m square, because m square is always a positive quantity. This has to be greater than or equal to 4, as mod of m is greater than or equal to 2 and both are positive quantities. So therefore mod of m square has to be greater than or equal to 4, which is strictly greater than 2, right? And therefore we see that f of m in this case also not equal to 2, in fact it is strictly greater than 2, and therefore f of m. So therefore we succeeded in producing at least one element in the codomain which do not have a pre-image, and therefore we have shown that f is not onto. By this, in fact, we have exhausted all the integers. So, how do we understand the onto function graphically? Given a graph of a onto function, how do we determine, given a graph of function, how do we determine whether it's onto or not? So, here we again use a horizontal line test. Now, here I am talking about the function from R to R. So, here the codomain is R. So, we see that the function is onto provided the range of this function is R itself. So, if range is R, that means you draw any horizontal line on this parallel to x axis cutting this y axis, it should intersect the graph at least once. If it does not do, then that means for that value of y, the given graph do not have a pre-image. No values of x from the x axis will form a pre-image for that y. So, therefore, the function f from R to R is onto if and only if every horizontal line intersects the graph of f at least once. Now, if f is say some R to A, where A is a subset of R, what I will do in that case, I will consider only that part of A on the y axis, and I would use this result for that part of y. So, for example, if I have this as my codomain, interval B to A, in that case I will see only the horizontal line in this stretch, not outside this. We do not have to, because the range of the function should lie in this interval A comma B. Okay. And so, the result should be true for all the horizontal line lying in this stretch only B to A. Okay. So, this is how we understand the onto function graphically given any graph. If every horizontal line given any graph of the function from f of the function whose codomain is R, if every horizontal line intersects the graph of f at least once, then we say that the given function is onto. So, with this we end up this session, and in the next session we are going to discuss the bijection and increasing and decreasing functions. Thank you for watching this, and have a nice day ahead.